we do that before?
Okay, as we begin, knowing we've got a test coming up next time, or half a test actually, I did post a review for the next test. So this is what you need to know how to do for Chapter 2 and Chapter 3. And there are some problems here that you can practice with. And this is quite a bit longer than what the actual test will be. But you see there's some applications problems. There will be at least 2 application problems on the test. So be sure that you check out that. And I will post the solutions to the review. I changed a couple of the problems, so the solutions that I have are not complete. So I need to modify those, but I will get those posted by tomorrow. So you'll be able to look at those too.
The exam is Tuesday.
The exam is Tuesday in class.
Is it online or paper?
It's going to be on paper this time. Because I can tell more about what you're doing if you actually do it on paper. And I've noticed too, a lot of the, especially in Chapter 2, that a lot of people were sending me messages saying, I just mistyped this, I left out the negative sign here or whatever, and it counted it wrong.
Especially with graphing.
Yeah, with graphing too, it's really difficult. So I went ahead and just made the decision to do the next test on paper.
And this test is only on Chapter 2, right?
The test itself on Tuesday is Chapter 2. Chapter 3 is take-home. Okay, and I will give it to you on Tuesday because we're going to finish Chapter 3 today, but then you'll have until the following class period to bring it back.
Okay.
So let's pick up with where we were last time, and we were working on a minimization problem. We had just gotten ready to start that one. We had just finished example 1, which was a maximization problem. And one of the things that you'll notice, we don't always have to do the equations with z every single time. We don't always have to do those green lines. The reason for doing those was to show you that z was increasing as you move outward. And what the corner point theorem actually tells you is that if you're trying to maximize, all you really have to do is substitute in the corner points. And if you substitute in the corner points, then you'll either find the maximum or the minimum. And I'll demonstrate that for you. In this problem, since we're doing a minimization problem, what you want to do is remember that z increases as we go outward still. But this is a minimization problem, not a maximization problem. So this time, we're going to be looking toward the lines toward the bottom. So let's look at this example. So we're going to do basically the same thing that we did last time. The fact that we have the constraints of x and y both are equal to or greater than 0 is just simply going to mean that we're going to only graph in the first quadrant. There's no need to show the rest of the quadrant, so we'll go ahead and lay out the graph grid in that way. We've now taken care of both of those. So we'll move on then and graph the two constraints, x plus 2y is equal to or greater than 10. So if we let x be 0, y is going to be 5 on the boundary line. If we let y be 0, then x is going to be 10. So we'll just plot those two intercepts. 0, 5, 1, 2, 3, 4, 5. And 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And since it says equal to or greater than, we'll use a solid line and draw the boundary. And then since it says equal to or greater than, if we test the point 0, 0, it's basically saying 0 plus 0 is equal to or greater than 10, which of course is not true. So we're going to shade the other direction.
Saying we could get the coordinate points from that equation, by just doing that. Every time we do that.
Yeah. If you're going to graph it by hand, that's the easiest way to do it. If you're going to graph it on the calculator, then you're going to have to solve it for y first.
Okay, can you show me how much I'm going to make that coordinate?
Okay. We're going to graph for the boundary for that constraint. We're going to graph the equation x plus 2y equals 10. Okay? So if we let x be 0, that basically makes x disappear. And then we have 2y equals 10, which means y is going to be 5. Okay? And then if we let y be 0, what we have left is that x equals 10. So that gives us the point 10, 0. Because if you're choosing 0, 0 as your test point, and you plug 0, 0 in here, you get a statement that 0 plus 2 times 0 is 0, and 0 is, in fact, not equal to or greater than 10. So we don't want to shade towards 0, 0. We shade to the other side. Okay? Does that work for everybody? I've got one more copy of the class notes up here if anybody doesn't have them.
I lost mine the other day, actually. Sorry.
So that gives us our first constraint. Our second constraint is 3x plus y is equal to or greater than 10. So again, we're going to graph the boundary. 3x plus y equals 10. And when we do that, if we let x be 0, that basically makes that part disappear and we have y equals 10. And if we let y be 0, then we have 3x equals 10, and that means x equals 10 over 3. And that's not necessarily a nice point, but we know that 10 over 3 is 3 and 1/3. So we can still get a fairly accurate place to, for that point. So 3 and 1/3 is 1, 2, 3, and not quite halfway. 10/3. And the other point is 0, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, we'll draw the boundary line. And so with this boundary line, if we test the point again, 0, 0, we see that that's not true. So we're not going to shade towards 0, 0. We're going to shade the other direction. So we see that we've got the feasible region is this area here. It's where everything is double shaded.
So, where you say no, because it's, 0 is not greater than or equal to 10, if that was, say, -10, then it would be shaded the other way?
It will be shaded the other direction.
Okay.
You're choosing your test point because this test point is on one side or the other of the line. And if this one doesn't work, then nothing else on that side is going to work.
Okay.
But if it does work, then everything on that side works.
Okay.
So all of your solutions are going to be in the region where I just put all the pink marks. Your corner points for that region are 10, 0, I'm sorry, and that's 0, 10, not 10, 0. And 10, 0 is the other corner point, but it's this one. But we also have one more corner point, right there. Point A. Now this is an unbounded region because that shading continues on out forever, but that's okay because we're trying to minimize the function, so we're going to be looking for a minimum value. And the corner point that's most likely to work is this point A. But we will test them all, but we first need to find what is the value of A. And the value of A, if you go back to your Chapter 2 methods and take these two boundaries, and solve that system, and you can solve this with matrices, that's part of the reason we do matrices first, then you can use the augmented matrix and have 1, 2, 10, 3, 1, 10, and store that in A and do the row reduced form of A. So we'll do that on the calculator. We'll make A into a 2x3 matrix and put the entries in. And then quit from there. Check that you've entered matrix A correctly, and we have. And and then go back to matrix, go over to math, do the row reduced echelon form of A. And see that X is 2 and Y is 4. So it's our other corner point. And then since the function that we want to minimize is this one, then we will take z is equal to 2x plus 4y. And see which one of those points actually provides the minimum value. So 2 times 10 is 20, plus 4 times 0 is 0, so this one's 20. 2 times 0 is 0, plus 4 times 10 is 40. 2 times 2 is 4, and 4 times 2 is 8, so 4 plus 8 is 12. And that is our minimum value of z. So the point A minimizes z. Get the calculator. So the solution for our problem was the point 2, 4 provides a minimum value say the minimum value of z is 12. And z might have been a cost function. And we were trying to minimize the cost of 2 different things that we were making. Okay? Now just a quick reminder of some language here. This is an unbounded feasible region. And because it's an unbounded feasible region, we could not maximize z. That would not have been possible because we don't have a closed corner point. And even though this is a minimum point and that is the maximum of the minimum points would occur here, that doesn't mean that if you move further out here, you don't get a larger value. In fact, you will. So we can only minimize that function. We cannot maximize it. And the problem that we did before, pull my notes back out. See the problem. That on PowerPoint. When we did this maximum problem, We could have minimized Z as well as maximizing it because it's still, this is a bounded feasible region. So you can get both a maximum and a minimum. But if you have an unbounded feasible region, sometimes you can only minimize and not maximize, or it's possible that you might maximize and not be able to minimize. It's also possible, let me make sure this is a different problem. What we just did. Yes, it is. It's also possible to have a feasible region that looks like this, and to realize that you could actually get a minimum value anywhere on this. Now this one didn't provide a minimum value, it provided a maximum value. But if we'd been trying to maximize, we couldn't have done it. And it is possible for the whole section to land on the edge. So this is what I was referring to when I said that we had a corner point theorem. You don't have to always draw these parallel lines. Just realize that as you increase Z, what you're doing is you're basically moving through the feasible region according to that equation for Z, and it's going to get larger as you move up and smaller as you move down toward the origin. So really the only thing you have to find is your corner points to find your optimum values, either maximum or minimum. So we will look at we'll look at one more example. So sketch the feasible region for the following set of constraints and then find the maximum and minimum values of the objective function. And our objective function this time is Z equals X plus 10Y. And our constraints are, we actually have 3. X plus 4y is equal to or greater than 12. X minus 2y has to be less than or equal to 0. And 2y minus x has to be less than or equal to 6. And for some reason, x has to be less than 6. So before I go on with the PowerPoint, we'll take our time and graph this one. So this is our objective function. Here's our constraints. X plus 4y is equal to or greater than 12. X minus 2y is less than or equal to 0. 2y minus 4 is less than or equal to 6. And x has to be equal to or less than 6. Now there's nothing here says that x has to be positive or y has to be positive. So we want to go ahead and graph so that we can see all the plots. And we'll begin with x plus 4y is equal to or greater than 12. Which gives us the point that if x is 0, y is going to be 3. And if y is 0, x is going to be 12. I didn't leave myself enough room, so I'm going to do this by saying 2, 4, 6, 8, 10, 12. And then 0, 3 would be right here. And we'll draw that line. So that was our first boundary. And again, when we check 0, 0, 0 plus 0 is 0. 0 is equal to or greater than 12 is not true. So we'll shade above the line. And then we'll move to the next constraint. If x is 0, y is 0. And if y is 0, x is 0, so since we have the origin, number one, we can't use it as a test point. That's a problem. And number two, we need another point on the line. So the only way that I'm going to have x minus 2y is equal to 0 is if x is equal to 2y. So if I were to pick x to be 1, well, let's pick y because that's easier. Let's pick y to be 1. 2 times 1 is 2, and x would be 2. So there's another point for us. So the first point is 0, 0, and the next point is 2, 1. And if you just want to be sure that you're doing it right, you could also say, well, let x be 2. And if x, or let y be 2. If you let y be 2, 2 times 2 is 4, and x is 4. So there's a third point, since we're not able to use 2 intercepts. And we'll draw that boundary. And again, what happens, can't choose 0, 0 for a test point. So rather than choosing 0, 0, I'm going to choose, let's say 2, 4. That's going to be my test point. So 2 minus 2 times 4 is 2 minus 8, which is negative 6. And negative 6 is in fact equal to or less than 0. So I'm going to shade that direction. And then my last constraint is, or my next constraint is 2y minus x is equal to or less than 6. So, being careful to notice they reversed x and y here. If I let x be 0, then 2y equals 6 tells me y would be 3. And if I let y be 0, then negative x is 6, and that means 6 is, or x is negative 6. So 0, 3, which we're already using, and negative 6, 0. 2, 4, 6. And I can test 0, 0 for this one, so I'll choose 0, 0. 0 minus 0 is equal to or less than 6 is true. And then I have one more constraint. And that is that x is equal to or less than 6. So 2, 4, 6. And that's just going to be a vertical line. And that's going to be that x is equal to or less than 6, it's going to go this direction. So my solutions are going to be everywhere that I see purple and pink and blue and green. So not here, not here, not here, not here, not here, not here, but only right in here. Only in that little bitty area right there. And we're going to need the corner points for that area. Again, we can find those by coming back up here and pairing up these equations. So if I pair up these two, I'm going to need the row reduced form of 1, 4, 12, 1, negative 2, 0. And that looks right, so I need the row reduced form of that. Picked the wrong one, sorry. Try again. So the solution there is 4, 2. And 4, 2 would be this point right here. And it isn't really a corner point. So we need this corner point. And that's where x is equal to or less than 6 crosses x plus 4y is equal to or greater than 12. So our matrix would look like this. That's actually x plus 0, y equals 6. So 1, 0, 6, and then 1, 4, 12. So that point is 6 and 1.5. That point right there. And we have this point. That point is 0, 3. So that's a corner point. And the only other one we don't have is this one, and that is where x is equal to or less than 6, or x equals 6, which is x plus 0y equals 6, and let's see, the green line is 2y minus x equals 6. Which we'll need to turn around into negative x plus 2y equals 6, and x plus 0y equals 6.
So can you use the calculator?
Yes, thank you. We'll move it over here. So that's going to give us, here's matrix A, this one. 1, 0, 6, negative 1, 2, 6. And all I'll need to do is go and change the second row of matrix A. So that should be negative 1, 2, 6, again, I'll quit do the row reduced form of A and see that x is 6 and y is 6. So this point is 6, 6. And since this point and this point lay on the same line, and it's the same, actually, this point is on the same line as these, then I don't really need to use all of those. So what I'll do is I'll only use this point, and this point. I won't use the 4, 2, because it's actually on that line. So then I want to maximize and minimize x plus 10y. So 6 plus 10 times 1.5 is, see, 10 times 1.5 is 15, and 15 plus 6 is 21. And then using 0, 3, I have 0 plus 10 times 3, and 0 plus 10 times 3 is 30. And then using 6, 6, I have 6 plus 10 times 6, and that's 60 plus 6 is 66. So here's what we found. So we want to both maximize and minimize, find both sets of values. The maximum value comes from using 6, 6. And the minimum value comes from using 6, 1.5. So Z is maximized at 6, 6, and Z is equal to 66, and Z is minimized at 6, 1.5, with Z equal 21. And I think you'll see from this particular problem why I said that I would let you do chapter 3 as a take-home. because that would be a really long problem to have to do on a test in class, because there's so much involved with solving that problem. So even though there were a lot of steps there, does anybody have any questions on how we did that? If you can do that one, you can probably do just about any of them. Okay, let's try one. And let's see. Then we'll go on. Let's see. I want to make sure we've got time. Yeah, I think we do. We have to do section 3.3 also. We've got 2 problems to do in it. This is find the maximum and minimum values for the objective function z equals 3x plus 4y on the region bounded by these constraints. So we have a whole bunch of constraints. And just for the sake of argument on this one, I'm actually going to graph this one on the calculator rather than doing it by hand, just to save time. You can graph it by hand if you want to do it. This time I'm going to do it on the calculator just to save time. I'm not going to do the shading, but I'm going to graph the lines. Because then I don't have to go through the matrices process to find your corner points. We can actually just look for intersections on the calculator. So this line, the boundary line, is going to be y equals negative 2x plus 5. This one is going to be x plus 5, or will translate to y equals, and I'm going to cheat a little bit here. I'm going to subtract x from both sides. And then I'm just going to divide by the number in front of y, which is 5. I'm not going to make all the fractions and stuff. Your calculator understands what that is just fine. And then this one is going to be y equals negative 2x plus 14. And this one, and again I'm going to cheat a little bit, is going to be y equals, move the x over to the other side, so it's going to be x plus 20, and then divide both sides by the 4. So I'm going to put it in that way. So let's get the calculator. On the calculator, I'm going to put in y equals negative 2x plus 5. In parentheses, negative x plus 16 divided by 5, negative 2x plus 14, and then in parentheses, x plus 20 divided by 4. And none of those constraints say that I have to be limited to the first quadrant, so I'm going to go to the window and make sure that I'm going from negative 10 to 10 in all directions. Now I'm going to graph. So there's my first boundary, there's my second boundary, there's my third boundary, there's my fourth boundary. Now, in order to pick out the region that I want to shade, I'm going to test 0, 0. Since 0, 0 is not on any of those lines, I'm going to test 0, 0 on all of those inequalities. 0 plus 0 is equal to or greater than 5. No. 0 plus 0 is equal to or greater than 16. No. 0 plus 0 is equal to or less than 14. Yes. 0 plus 0 is equal to or less than 20. Yes. So what that means is 0, 0 works for two of these equations, but not for the other two. So I'm going to hit my trace button so I can tell which ones are which, and I'm going to use this calculator to help me sketch that region. And I'm not going to be perfect on my points. So that first line is the one that's going through this way. Now remember, I'm just sketching. I'm not trying to make this perfect. Let's see. Let's keep it relatively small. This one shades this way. I'm not actually going to shade till the very end. So then I'm going to jump to another one and see which line that is. Okay, that's a line that looks like it's one kind of this way. And 0, 0 doesn't work for it either. So that means I'm going to shade this direction. So far, I'm looking at this area. Then I'm going to move to this line. I'm going to have to trace around a little bit to see. There we go. Okay, so that one's almost parallel to this one. And 0, 0 did work for that one. So I'm going to shade this direction. So right now, it's looking like this area. And then the last one is going to be the one that's traveling uphill. And 0, 0 does work for it. So let's see if we can figure out where the feasible region is here. It has to be in between these two. It has to come down from here. It has to go up from there. So it looks to me like the feasible region is there. It is a bounded feasible region. And we'll have 1, 2, 3, 4 corner points. And we're going to have to be really careful how we find these because we're going to use the calculator to find them. So we're going to go second calc. Choose intersect. And I want to find this one first, so that's one of the lines. And that's the other line. And that's the point 1, 3. So So one of my corner points is 1, 3. And then I'm going to second, calc again, go down and choose intersect. And I've already found that one, so I want to find this one. So I'm going to move up to that line and say, yes, that's one of them. And since I'm finding that one, this is the other one. Let's make sure this is the other one. Yeah, that's the other one. And that's the 0.05. And then I think I'm going to find this one out here. So second, trace, number 5. Okay, that's not the line I want. That's not the line I want. Okay, that's one of them. That's not the other one. And keep hitting the wrong button. And that one. And that one. And that's the 0.46. Got one more. So I want to find this one. Move it out where I'll actually find the one I want. That's not it. That's one of them. And that's the other one. So there's the 0.62. And now I'm going to use the calculator even further to help me. I'm going to go to the table setup and make sure that it's set to independent is let me ask, and then tell me what the dependent is. Wait, I don't know if I can use the table up here or not. No, I can't. Darn it. I was going to use the table to do my calculations, but I can't do that. So I guess we'll have to do it by hand. So here's our objective function. 3x plus 4y. So 3 times 1 plus 4 times 3. 3 plus 12 is 13. 3 times 0 plus 4 times 5 is 20. 3 times 4 plus 4 times 6 is 12 plus 24, which is 36. And 3 times 6 plus 4 times 2 is 18 plus 8, which is 26. So our maximum value comes from there. And our minimum value comes from there. Okay? questions? We'll probably use the calculator to help us as much as we can on the applications problems, just so that we can go a little bit faster. So here's our first application problem. And what makes these a little bit harder is we're actually going to have to come up with the objective functions. And I think at this point I'll probably go ahead and switch to the PowerPoint and use it. So when you draw your graphs here, don't worry about them being perfect. Do what I did on that last one. Just sketch what it looks like from what we've got here. So here's our first example. Thomas Pinedo plans to start a new business called River Explorers, which is going to rent canoes and kayaks to people to travel 10 miles down the Clarion River in Cooks Forest State Park. He has $45,000 to purchase new boats. He can buy the canoes for $600 each and kayaks for $750 each, and his facility can hold up to 65 boats. The canoes will rent for $25 a day, and the kayaks are going to rent for $30 a day. How many canoes and how many kayaks should he buy to earn the most revenue if the boats can be rented every day? The first thing you're going to want to do is you're going to want to set up a table like the one that's on your handout. The number of boats are going to be your variables. So canoes will be X and kayaks will be Y. And it says his facility can hold up to 65 boats, so he can't have that to be any more, the total can't be any more than 65, so that's equal to or less than 65. The cost is $600 to buy a canoe and $750 to buy kayaks. So 600 times X plus 750 times Y has to be equal to or less than $45,000 because that's all the money he has. The last one about the revenue is actually going to give us our objective function because his revenue is going to be 25 times X plus 30 times Y. And he's going to want to maximize that because he wants to earn the most revenue. So this is how the equations work. X plus Y has to be equal to or less than 65 because that's all the kayaks and canoes that he can hold at his facility. He has $45,000 to spend, so 600 times the number of canoes and 750 times the number of kayaks is added together, and it has to be equal to or less than $45,000. If you divide the second equation through by 150, it'll give you an equivalent system. That way you don't have to deal with such a large number. You could do it, but it's probably easier just to give you an equivalent value if you divide through this whole equation by 150, which is the greatest common denominator of 45,000, 750, and 600. So that gives you a little easier equation to graph. And since the number of boats can't be negative, X has to be equal to or greater than 0, and Y has to be equal to or greater than 0. Applications problems almost always will have those two constraints. Since Z represents the revenue is going to be $25 per day for canoes and $30 a day for kayaks. Anybody have any questions so far? And once again, this change from this equation to this one is not absolutely necessary, but it sure does make the math easier. When you graph that, and again, I would graph it on the calculator. When you graph that, this is what it looks like. And if you want to know what I would put in on the calculator using my little shortcut, I will go ahead and show you that much of it. the first equation, x plus y equals 65, is going to be easy. Because that's going to be y equals 65 minus x. The second equation, 4x plus 5y equals 300, is going to be y equals, in parentheses, 300 minus 4x, close parentheses, and divide by the number in front of y, which is 5. And that'll give me those equations. And then the way I'm going to handle the restrictions of the first quadrant is I'm going to tell it x can't be less than 0. And y can't be less than 0. And since I, without seeing this graph, would have no idea how big to make x, I'd probably go with about 100, since we're talking about some rather large numbers. And then zoom 0, the zoom fit, and it'll actually find out the rest of what I needed to know. So what I see there is that I have the same general graph that they do. And I can find the value of the first corner point, which is 0.60, which is the y-intercept there, by going to calculator and choosing the value x equals 0. And it tells me that point is 0.60. That should be, I'm on the wrong equation. So that point is 0.60. This point is 0.65 to north of it. And then if I want to find the y-intercept, I could find it by using the root function or the 0 function. So I'm going to trace over close to it. And since that one, the first one, is the one that I want, I'm going to hit enter, then get below the y-axis, hit enter again, and it tells me that this point is 65, 0. And then the last point that I want is the intersection. And that gives me the point 2540. So you can use your calculator to help you find all these. So now that we've got the feasible region, now that we have the feasible region, we know that our corner points are 0.60, 2540, 65, 0, and 0, 0, because the feasible region is all towards 0, 0, as it turns out. So all we need to do then is list the corner points and plug in the different values of x and y into the equation for revenue. And of course, 0, 0 means you don't make anything. So we don't want that, but we want to maximize the revenue. If you get 65 canoes and no kayaks, your revenue is $16.25. If you get no canoes and 60 kayaks, your revenue is $1,800. If you get 25 canoes and 40 kayaks, your revenue is $18.25. So your best deal is to buy 25 canoes and 40 kayaks and make the maximum revenue. Now I'll give you time to fill in your notes for a second, see if you have any questions. It's the same exact process as we had before. The only new step is you have to come up with the equations. Questions? And this PowerPoint is in D2L, so if you need to go back and look at it again, fill in your notes. You're okay with that. And I think I'll skip over the your turn problem and go straight to the manufacturer. Well, no, let's go ahead and talk about the your turn problem because it actually refers to a previous example that we did. So I'll talk about it, but I won't walk you through it. If you go back to the example that we did in example 7 in section 3.1, if you still got your notes in front of you, you can look at that graph. So if you go back to that, and suppose that the company earns 20 in profit for every batch of cake cones and 30 for every batch of sugar cones, how many batches of each one should the company make to maximize their profit? This is the graph we already had. Our corner points are 6, 0, and 0, 6, and whatever that is. We didn't find what that corner point was. So we're going to need to find the corner point. I'm going to do that like I did before. I'm going to actually just graph these. The red line and the blue line are x plus 2y equals 12. So y is going to be 12 minus x divided by 2. And 2x plus y is equal to or less than 12 is going to be 12 minus 2x. And since I know it's in the first quadrant, I'll go 0 to 10. And hit graph. And find that intersection point. So the intersection point's 4, 4. So I'll switch to your notes here and we'll figure this out. So given those 3 corner points, and they make 20 on a batch of cake cones, I think it was, and 30 on a batch of sugar cones. And they want to maximize Z. If they make no cake and 6 sugar, that's 18. If they make all cake and no sugar, that should be at 180, not 18. And that will be 20 times 6, which is 120. But if they make 4 of each, they'll make 200. So their maximum is to make 4 batches of each. And our last one is a manufacturing problem. Happy Ice Cream Cone Company makes cake cones and sugar cones. That's this problem here. So if you want to go back and find that one, that's the one we did in section 3.1. I put it on here so that you have it as a reference. Your last application problem is about farm animals. And then we will be done. And if you have questions, we'll still have time for those questions on Monday. So you have a 4-H member that raises goats and pigs, and she wants to raise 16 animals, no more than 10 goats. So no more than 16 animals. She's willing to raise less. She spends $25 to raise a goat and $75 to raise a pig, and she has $900 to spend on her project. Every goat produces $12 in profit, and every pig produces $40. How many goats and how many pigs should she raise to maximize her profit? The solution is to first set up a table that shows the information in the problem. And then use the table to write the constraints. So this is the table. X plus Y has to be equal to or less than 16. X has to be equal to or less than 10. And her cost for raising is 25X plus 75Y has to be equal to or less than the $900 she's got to spend. And her profit is $12 times the goats plus $40 times the pigs. So this is what her system looks like. This is her profit function. This is she has to raise no less than 16 animals. X needs to stay equal to or less than 10. Both of them have to be positive because she has to raise something. And this is her cost equation that's been scaled. Basically, we just divided through so that we had a coefficient of 1 for X. So when we graph it, this is what the feasible region looks like. And we need the corner points. Obviously, 0, 0 is not going to give you a maximum of anything. So it's either going to be all goats or all pigs, or 6 goats and 10, or let's see goats comes first. So 6 goats or 10 pigs, or 10 goats and 6 pigs are the other corner points. And the maximum occurs at 0, 12, so she is going to raise 12 pigs and no goats. Because we like bacon better than we like goats. Okay? So that's the table that shows how she got her maximum profit. See you on Tuesday. We will have a little bit of time if you need to ask questions on Tuesday before you leave on chapter 3. You'll have time to do that. If anybody's still missing your first test,